Hello everyone, welcome to AI Anytime, the channel where we explore the fascinating world of artificial intelligence. In today's video, we have an exciting topic to discuss: detecting the likelihood of a voice being AI generated. We all see, right, as AI technology continue to advance, deepfake audio and generative models have become more prevalent. Now it's essential to have tools that can help us identify whether a voice recording is created by AI or not. In this video, we'll walk through the process of building a Streamlit application that you can see on my screen currently, that can provide us with a signal indicating the probability of an audio clip being AI generated. So let me first show you a demo that how it's works. So here I'm just gonna upload some of the audio files. You can see I've uploaded an audio called samoutput.mp3. This audio is the same audio that you can just see it over here. Okay, the video that I've created, I think last month, where I've created a deepfake video of me having a conversation with OpenAI CEO Sam Altman. Okay, I have end-to-end created this deepfake with voice cloning and video and everything over here. But if you want to create a similar deepfake, please go ahead and watch this video. Okay, so if I play this, you can see. Let me just go a little back. You can see Sam Altman is talking. So what I have done, I have taken this video, extracted the audio out of it. I have used a command line utility tool called ffmpeg that you can see it over here, and I have extracted that part of the audio. Okay, so if you come over here, now you will see this is the audio that I have uploaded called samoutput.mp3. So if I can play this audio over here, let me just go through here and music and just play Sam output. So this is the audio that we have.
Thanks for having me.
Taken. Yeah.
Generative artificial intelligence will continue.
So you can also listen to that on the same Streamlit application. When I click on analyze voice, what it will do, it will give you a likelihood of this video being AI generated, and it will also give you you can also listen to that audio there, and it will also give you a plot, a chart basically with the waveform there. So let's go and click on analyze voice. So when I hit on analyze voice, you can see it says result probability 0.98. The uploaded audio is 98.51. So we have rounded it off, likely to be AI generated. And you can also listen to the same audio over here.
I think generative artificial intelligence will continue.
And I have basically done voice cloning there in that video that I'm just I was just showing you the conversation with OpenAI CEO Sam Altman. Okay, so I've uploaded that audio, and the tool is able to basically detect the probability of that voice to be an AI generated. And we also have a disclaimer, that this classification or detection mechanisms are not always accurate. They should be considered as signals and not the ultimate decision makers. Okay, you cannot just completely rely on this tool. Okay, so this is what it does guys. So if you see this, okay, a Donald Trump's video. Okay, so this is not being generated by AI. Trump is talking about something. Let me just play this.
But Mr. Trump, you're not a nice person.
So if I've taken the same audio here, okay, extracted it from some tool on YouTube, and I'm just going to upload. This I've cut it short. You can see that we have here Trump cut. So I'll just use Trump cut here, and when I upload Trump cut audio, you will be able to see the result for this particular audio, and it says the uploaded audio is 0% likely to be AI generated. Okay, in this case, and you can just listen to that audio here again, and I can just listen to this when I click on this.
For President of the United States.
So you can see he's talking something, and you can just record it over here. And this is the disclaimer. So this is what we are going to build in this video, guys. Okay, so this tool that we are going to build, we are going to reverse engineer the process of voice cloning or custom text to speech, how we can use those classifiers. Basically that's what I'm going to do. So let's build this now, guys. So if you see, I'm currently on a GitHub repository called Tortoise TTS, which is a short form of text to speech. I have created couple of videos on Tortoise TTS, that how you can leverage this open source model for text to speech. It also provides you voice cloning capabilities. If you have some kind of voice and you want to create custom voice on top of that, you can leverage Tortoise TTS. Okay, so this basically helps you generate voices. Okay, but what if we have to find out if those voices are being generated by an AI or not? This is mainly a autoregressive model. It uses autoregressive features. I will explain that in a bit. It is very important to understand. And if you come down in the below section, they have an option called, if I show you, they have an option called Tortoise detect. So they have trained a classifier, okay, and we are going to use that classifier. And if you go ahead and use this current code, that the file, it might give you some bugs. There are bugs in this file. It is from Tortoise Py. I have done some changes. Of course, I will cover that when I'm writing the code for that. So Tortoise TTS is very famous when it comes to custom voice cloning, or generating custom voices from your sample voice or a reference voice. You can generate some voices. Okay, so this is Tortoise TTS. They're also available on Hugging Face. You can see Tortoise TTS. There are version 2 version. This is very good. I have also used in this video a conversation with OpenAI CEO Sam Altman, where I have created Sam Altman voice using a sample voice of Sam, after leveraging this Tortoise TTS. Okay, and I got a very similar or near voice of Sam Altman. Okay, how does this work, guys? If we talk about Tortoise TTS, let's understand that in a example. Okay, that how it helps to how we can build it, and how an autoregressive model basically helps you. Okay, so let me just write it over here. I'm just writing it, an autoregressive model. Autoregressive model. What kind of role it plays, okay, when we are basically, let me just make it bigger so you can have a look. Autoregressive model, let's divide that in chunks to understand how Tortoise TTS basically works, or mainly in the context of voice cloning for text to speech. Okay, mainly for text to speech. So let me just write it over here. This is important to understand before writing the code. Anyway, you will get the code from GitHub repository. If you are not interested in the intuition behind it, please go ahead and just take the code from GitHub and run it off. Now, if you see, here is an example. For just take this as an example. Hello, how are you? This is the example. How can we generate the speech out of it? There are some steps that you have to understand, which is important to understand as well. The first thing is encoding the text. So the input text that you see, let me just make it round so you can just separate this. Encoding the text. So the input text is basically encoded into a numerical representation that the autoregressive model can process. It's basically a statistical term. I'll explain that. So now, for simplicity, if you see this, for example, let me just write 8, can be anything, right? 12, 15. This is basically a character level representation, guys. So if I just go like this, 15 and 21, this is nothing but the character level representation of the above sentence that we have. So character level representation. This is just to help you understand in a very layman term, character level representation. The first thing is that encoded text. Now you have the encoded text. What next is a sequential generation, or the sequence generation. The next step is sequential generation. Now these are important to understand the reason, because when I'm writing the code, when we reverse engineer this process of text to speech, we'll see something like encoder. We'll use auto mini encoder of Tortoise TTS. We'll use that class. So it's very important to understand how it's working. Then only we'll be able to understand how are we reversing it, the reverse engineering that we are going to do. So when it comes to sequential generation, okay, the autoregressive model that we are talking about starts by predicting the first speech waveform sample based on the encoded text. Now we have the encoded text. This is our encoded text now. Okay, so now let's assume, let me just write it off for you. So let's assume the model predicts a waveform sample with value 0. So what will be the generated waveform sample, guys? So generated waveform sample will be generated waveform sample will be your 0. Okay. Now to generate the next sample, the model conditions its prediction on both the encoded text and previously generated sample. Okay. Now when we look for the next waveform, what does it do for the next waveform? So for the next waveform, it considers this, and it also considers this, okay, that encoded text, and then it gives you the next waveform samples. Now suppose, for example, this is how, for example, we can denote it, okay, 0 and 0.3. Now the model continues this process. This will go on till n process, predicting each waveform sample based on the text and the previously generated samples. Now for the next one, it will rely on both of this and also on the encoding the text that we have, this part here, this part that you see. Okay, so this is on the sequential generation for the sequences. Now when we go for the next, it is nothing but the feedback loop. Now in this kind of autoregressive model, the feedback loop refers to the process of using previously generated samples as context for generating subsequent samples. Now, this allows the model to capture dependencies and generate coherent speech. So for generating the coherent speech, now let's say the model has generated, for example, this waveform sample 0, or maybe let me just do, for example, suppose 0.2, 0.4, 0.1. If this is your waveform sample, when generating the next sample, the model takes into account these previously generated samples along with the encoded text to make the predictions, okay, in a feedback for generating the coherent speeches. Okay. Now the next step is the most important step, I'll say, is the sampling or greedy decoding. So I hope that you are aware about sampling, isn't it? So when using sampling, the model basically predicts a probability distribution, okay, over possible values for the next sample. Okay, sampling has been used for predicting the probability distribution. It then samples a value from all those distribution. For example, if probability distribution, how that model predicts a probability distribution of, for example, the same thing. For example, if we have 0.2, 0.4, 0.1, how does now model predicts the probability distribution of this? That's where sampling or greedy decoding is being used, guys, in when we talk about Tortoise TTS or any similar text-to-speech model. Okay, so for the next sample, it might randomly choose the value you don't know. For example 2, it randomly can choose it, okay, to index 2 in the distribution. For example, this is basically index 2 in the distribution or distribution list or distribution, and this can be selected as the next sample. Okay, so this introduces some randomness. So when we talk about sampling, or basically when we talk about sampling, not the greedy decoding, let's talk about sampling. This basically introduces here randomness, and this features is very important. When we are using sampling while text to speech, when we reverse engineering it, we can look at the randomness of basically look at the randomness or variations in the generated speech to find out if there are any randomness into it or any for example variations into it. We can look at this physical property or the property of that generated speech to find out if those are being generated by AI or not. These are the features that helps us detect that, guys. Okay, and that's where when we are doing text to speech, when creating this kind of model, sampling has been introduced by the model when we talk about the autoregressive model. Okay, and these are not the only architecture to train models when we talk about text to speech, because autoregressive is more of a statistical feature, guys. Now when we sampling or greedy decoding. So greedy decoding is kind of very similar. The way it works, basically, greedy decoding tends to produce more deterministic output, guys. It's more deterministic when you talk about it. Okay, so the last one is called something called iterative generation. So it's an iterative process. So iterative generation. So the autoregressive model that we are talking about, right? It iteratively generates a speech waveform samples until it reaches the desired length. Okay, until it reaches the desired length of the synthesized waveform. That's called iterative generation. So it conditions its predictions on the previously generated samples and the encoded text at each step, gradually constructing the entire waveform. Okay, and the length of the waveform depends on factors such as, for example, what are the factors that in very layman terms, the factors we talk about is that can be duration of the input text, and the desired duration of synthesized speech. So that can be, for example, desired duration of the synthesized speech. So these are the 5 steps when we are trying to create a text to speech model, encoding the text, sequential generation from that encoded features, then we have feedback loop, then we have sampling or greedy decoding. Sampling basically introduces some kind of randomness into it, and then we have iterative generation on a very high level, guys, right? So throughout this, we talk about throughout this iterative process, the autoregressive model leverages this feedback loop. Feedback loop is very important. Okay, feedback loop and sampling or greedy decoding. Okay, so the model's ability to capture dependencies and generate coherent speeches improve as it incorporates more context and progresses through the generation process, guys. Now this is the way basically it. Let me just minimize this. If you go through the research paper as well, the Tortoise TTS, it's also available on Replicate, guys. Okay, if you want to use this, please go ahead and use Replicate as well. They provide some free sample. You can see it. They have many versions. When they started initially, now they're also using CVVP model. You can go through and read on the research paper. Very, very interesting to go through and read it. So this is on how you generate text to speech, but we are more interested in if you come here in Tortoise, they have is this from Tortoise Py. Okay, Tortoise .py. Okay, so if you see, they are using utils audio and load audio, and from API import classify audio. So if you go to API, where is that API, guys? Okay, the API.py. Now from API.py, if you come over here, and this code will be given in the description. See, this is the Hugging Face classifier path, the checkpoint. We need this file classifier.pth. I'll give this link in description as well. You can download and you can test it out as well. Now if you come down, they have something called, see, we're talking about autoregressive output, isn't it? So that step has been covered, and they have this classify audio clip. Now if you see this classify audio clip, this is a class we are going to leverage, and this class has something called auto mini encoder with classifier header. Okay, which is again very important to understand, because this is what it's going to help you get the result there, guys, this class basically. So we'll also understand this. Okay, so let me just write it in a very high level overview so you can understand. Okay, so we are going to use this classifier class auto mini encoder with classifier head. So I know I don't know if you are aware about encoding or encoder. So imagine you have a neural network model for speech recognition. Okay, so the encoder component of that speech recognition model. So when I'm just writing here speech recognition, I'm just writing speech rec. for example. So the encoder component of this model takes an input audio waveform. So we have some waveform, for example, some input waveform. Okay, I'm drawing here, sorry. Input waveform, speech recognition, and then we have input audio waveform, such as that can be spoken sentences. Sorry for the background noise, guys. I'm currently on travel, that's why I have to create these videos in some constraints and challenges. Okay, so input waveform, so we have spoken sentences. So encoder basically helps you process this to extract relevant features. It helps you extract relevant features. And what are those features? When we talk about speech recognition, so let me just write it, relevant features. So when we talk about these relevant features in speech recognition, they are nothing but, let's take example, that can be your pitch. This can be pitch, this can be, for example, rhythm, this can be your spectral content, this can be different type of features, and that's where this helps. Okay, when we're talking about encoder. Okay, this is only talking about encoder right now. We are not talking about the classifier head. Okay, now this is an example, and it may identify specific phonemes. Now phonemes is again very important. I have covered phonemes in my tutorial video of bark. I have a video of bark, again a new model for text to speech. You can go through that video. I have covered phonemes in very much detail. Okay, so now the encoder may identify specific phonemes within the audio waveform, the waveform that you see here. Okay, and represent them as embeddings. Okay, so let me just write it over here, embeddings. Okay, represent them as, these embeddings are nothing but the lower dimensional representation, guys. Okay, they are in lower dimensional representation that encode the phonetic information of the speech. Every language had different type of phonemes as well now. Okay, English has some other phonemes, and others. These are all by I think managed by an organization as well for all these phonemes. Okay, now the encoder learns to extract this meaningful representation by training on a large data set of labeled audio samples. Okay, so labeled audio samples. Okay, where the correct transcriptions or labels are of course provided. Throughout this training process, the encoder learns to capture relevant speech features that are useful for that speech recognition task. That on the encoder part of it currently. Now what are we talking about? Classifier head here. Okay, what is classifier head? You see this class, the class that we are going to use on Tortoise TTS. Okay, that this classifier that we will download from Hugging Face, we already have downloaded, and this class classify audio clip, where we are passing the clip. These are nothing but the torch tensor, okay, of that audio, and we're going to pass that, and when we are going to leverage this audio mini encoder with classifier head. Okay, what does it mean, guys? What does we understand by classifier head? Okay, so if you come down here, so classifier head, right, it's a part of neural network that follows the encoder. So it takes the encoded speech. For example, if you have your encoded speech feature, I'm just writing it over here. I hope you can see it, encoded speech feature. So it takes the feature from the encoder and performs classification. So it performs classification. Classification to determine what the spoken words are. So this is what classifier head is being used with that auto mini encoder, okay, in Tortoise TTS. Okay, so for instance, the classifier head can consist of additional layers as well. Okay, additional layers and operations that process the encoded speech features. It may include fully connected layers. You don't know, because it depends on the architecture, of course, what kind of architecture has been used. Okay, so it can have fully connected layers. For example, fully connected layers and activation functions. Please go through the research paper, and let me know your thoughts on the comment box as well. These activation functions, basically to map the encoded features, okay, to the specific classes or words in the speech recognition task. So by combining both encoder and classifier head, The speech recognition model can take an input audio waveform, extract the relevant speech features through the encoder, and then classify those features using the classifier head to determine the spoken words, guys. So overall, the encoder helps capture a representation of the waveform, while the classifier head leverages those representations to perform the specific classification, such as speech recognition. Now, enough of theory, guys. Enough of the theoretical or theoretical knowledge or intuition behind it. I hope you may find this interesting. Let me know your thoughts on this, guys. I'll be more than happy to discuss. Now, let's write some code, guys, and let's develop the application that I have shown you in the beginning of the video, the Streamlit application. Okay, we're going to build that. Maybe let me first open my gist here. Okay, so I'll just go and I'll go on my GitHub. Basically, I'll go to here on my your gist, and in gist I will take couple of function. You can see I have couple of function over here, load audio and classify audio, because I'm not going to write the entire code from scratch. Okay, so I will give this link in the description, okay, for Tortoise TTS. Now I'll go to VS Code, and first what I have to do, I have to go inside desktop. I have a folder called voice AI. I have a virtual environment. So let me do one thing. Let me open in terminal, and in this terminal I will go inside cd cd scripts /activate. as I'm on PowerShell. If you are on Linux machine, you have to go inside bin and activate it. Now a couple of cd clear, and here I am already in VS Code. Let me explain. I have cloned the repository, but you do not need to have to do that, because we don't need all the files. Okay, the files that you see I already have shown you there on the GitHub repository. Now in app.py, let's start writing the code. The first thing that we have to do is import Streamlit thingy over here. So import Streamlit as st. If you are not aware about Streamlit is a web framework in Python to build data science apps, guys. So you can go on streamlit.io or something and find out the documentation. I think it's doc.streamlit.io. Okay, now import Streamlit as st. We need couple of imports here, or more than that. Import OS, and we need from Tortoise, what is that? I think it's inside models. So from Tortoise and then models, and here is the classifier. Okay, so Tortoise dot models dot classifier. I hope I spelled it right, Tortoise thing at least. And I'm just gonna import here audio mini encoder. It should show me here, guys. Okay, so audio mini encoder with classifier head. Yes, this is what we are going to use. Now let's have some utility thing here, guys. Okay, to have file extension, etc. We need IO as well. We need Librosa. Okay, what did I do here? Just let me do a Control G. Okay, sorry. Okay, let me just close this. Not required. From import IO, and then we need Librosa. So import Librosa, because we are going to plot some waveforms using Plotly Express. Import Plotly dot express, I guess. Yes, as what is that? PX. Let's have something here. We need torch here. Torch is our backend, guys. So import torch, and we need some functional. So import torch dot neural network dot functional import f torch dot nn dot functional. I think not import. Let's make it a short name as f, and we need torch audio as well. Of course, we are dealing with an audio data. Import torch audio, and we need numpy for mathematical computation. So import numpy as np, and from scipy, so from scipy.io.web file. I don't know if we are dealing with web file yet, but let's have it. So import read, and this makes sense. Now we are done with the imports, guys. But for that, what you have to do, you have to do this requirements txt. We have to install all these dependencies. We have tqdm, transformers, tokenizers. We have scipy, Librosa, Numba. If you are on CUDA and stuff, you can have a look at that. We need ffmpeg, a command line utility tool, or library. We need torch audio. So we need all these things, guys. Okay. Now if you come back on app.py, here let's have that couple of functions. So the first function that I'm going to take is load audio. That will help us load the audio. So let me just copy this here. load audio. This is a very simple function, pretty much self-explanatory. We are only looking at MP3. We are converting it to bytes IO, okay, the input file content, and then we have some sampling rate, which is currently on 22,000. You can increase that to 48, 24, whatever you want to do that. Maybe you can play around it. So this is what we are doing with the load audio here. It loads the function, loads the audio. So let me just write it over here. Function to load the audio file, and now the next function that I will write is the classifier, function for classifier. And here we go. So we'll go back on the gist and we'll take classify audio clip. So let's take that classify audio clip. What I'm going to do here, I'm just going to copy it. So classify audio clip, and the same code, right? Auto mini encoder with classifier. You can see it says returns whether or not the classifier thinks the given clip came from AI generation. Parameter clip, it's a torch tensor I discussed earlier, combining audio waveform data. The probability of the audio clip being AI generated, that's what it returns, the probability of the audio clip. So we have this comment over here. We have some parameters, the embedding dimensions, the downsample factor. I have discussed that, guys. I hope you got some information from sampling, greedy decoding, embeddings, all this function that I have all this factor that I have discussed. Okay, so I hope you got something from there. Then we are using this classifier.pth, the checkpoint. You can see I have downloaded it from Hugging Face. I'll give the link in the description. You can also download it. And we are using a CPU machine. You can run this on CPU without any problem. And then we are just passing a softmax function to find out the maximum value there, and then we are returning the result. This is the classify audio clip. Now let's write the Streamlit thing here, guys. So the first thing I always do, I use the page layout, st.page config, and I use layout equals wide. So let me just do a wide here for now, and let's have a main function. So let's write this inside a main function, and here let's start writing our code for the UI, guys. So let's give a title. So st.title, and the titles would be, maybe you can write something AI generated voice detection or something. Okay, voice detection. And now let's give this if underscore name underscore main, and this would be the main. Okay, this looks good. Now, so let's have a file uploader. So let me just comment it out. So we have a file uploader, and in the file uploader, the first thing that we do, let's have a variable uploaded file that will store that audio file. And here we are going to do st.file uploader, and in this we'll write something like upload an audio file or something, upload an audio file, and the type is mp3 for now. Let's have mp3. You can also use web file if you want, and let's have, for example, for now it looks good. So if uploaded file is not none, we are checking if there's a value inside it, there's a file inside it. So if uploaded file is not none, let's have a button, guys. So I'm just going to have a button called if st.button analyze audio, and then again we'll start writing code inside it. So let's have 3 columns. I need a column. So column 1, column 2, column 3, and st.columns. I'm dividing the layout in 3 columns, giving equal weight to all of them. Let's pass that at 3, and with column 1, here I will write the code for column 1. So my column 1 thing is nothing but first an info message. So st.info, let's have something like your results are below or something. Okay, st.info. So let's have, or maybe we can show that in the result in the first column only. So load and classify the audio file. Okay, and load and classify the audio file. Let me just go a little up. Load and classify the audio file. So first thing is audio underscore clip, and in audio underscore clip we're going to use that function, guys. What was the function name? Load audio, isn't it? So load audio, yes. So load audio, and the path is uploaded file. sorry, uploaded file. This is strange. Uploaded file. Okay, this is the file, uploaded file, audio clip, and our result should be in this result. We're going to use classify audio clip function. Let's pass this audio clip now. So audio clip, audio underscore clip, audio underscore clip, yes. So result is in result. Now we only have to get the torch value there, the probability value, because it gives you some torch tensor. So maybe we can use the item there. So result item. Okay, this looks good. And now let's print that. So I'm going to use the info message. I'm just going to say result probability or something. Result probability, and with something like this. Okay, so result probability. This will not be colon end here, guys. So the parenthesis. Okay, and here we're gonna write in quotation result. Now ht dot success, and here we're gonna write our success. So let's have the uploaded audio is, maybe for example, result, and then we'll multiply with 100 to print that on a level of 100%, point up to rounding to 2, and this looks good. Maybe likely or something. Let's likely to be AI generated, likely to be AI generated, and we close this. Let me put also a full stop. Here we will not have this. This looks nice. So we are done with the column 1, guys. Let's quickly write the column 2. So with column 2, in column 2 we're gonna print the file name, for example. Okay, or we can also draw the waveform. Okay, so let's do that with plotly. So ht.info, and it should be not your results are below. Let's write something, your uploaded audio. Maybe we can print the name also, and we can also have an audio player that comes with ht.audio, I guess. So your uploaded audio is below ht.info, and then in ht.audio we'll have uploaded file. Yes, this looks good. Not result, we need only uploaded file here, ht.audio. And now let's create a waveform. So I'm just writing it over here for you. Create a waveform plot, for example. Then we first, what we have to do, let's have a fig px.line. This is coming from Plotly Express. I love Plotly, guys. Fig dot add scatter. You can also use matplotlib, for example, if you want, but this provides a little bit more interactivity. Add scatter x list, and there should be a range of it. So range, length of the clip, so length of the audio clip, let's squeeze this. So squeeze, why I'm not getting that, squeeze, and this is the method, and then would not need this, guys. Y equals audio clip dot squeeze as well. Audio clip dot squeeze, yes. Again, this is a method, and this looks good. Okay, add scatter. Now let's update. So update layout, which is again a method. Inside this we're gonna write title. So title is nothing but, for example, waveform plot or something. Waveform plot, comma, then it goes the x-axis. So x-axis, and let's title, I think it's x-axis title, yes. And this, let's have time on the x-axis, and on the y-axis, we will have amplitude, yes. And then we just use ht.plotly chart, a streamlit method. So what is that? ht.plotly chart, and we're just gonna do fig, and I'm going to use a parameter called use container width because we are using column. I want to keep that as true. Now we are done with our code, guys. Let's have a disclaimer. I want to use a disclaimer that this should not be your go-to tool for finding out if an audio or a voice sample, basically the voice sample, not an audio, because we are not doing it for music and all. Okay, this is mainly for voice samples. So this will not be your go-to tool for the making a decision if a voice sample is being generated by an AI or not. Okay, so warning, for example, we can write something like this classification or detection mechanism, for example, detection mechanisms are not, mechanism spelling is wrong, I guess. Mechanisms are not always accurate. They should be considered maybe as a strong signal and not the ultimate decision maker. Let me do an Alt G so we can manage this out. I think we are done with the code, guys. So let's do one thing now. Let's run this. So for that we have to do streamlit run app.py. So I'm just going to do streamlit run app.py here. Now when I do that, what it will do, it will open, you can see, in a new tab, and we get something called AI generated voice detection, guys, a Streamlit application. So you can upload your audio file and the tool will do the rest. It will tell you whether your uploaded audio or voice sample is being generated by or AI model or not, because we are living in the new normal of generative AI. You are generating data, all kind of data, that is video, that is image using Midjourney, Stable Diffusion, DALL-E, video using Gen 2, we are generating music using Music LM, we are generating voice using Bark or Tortoise TTS, or lot of other tools are there. We upload SAM output here, guys. We have a button called Analyze Audio. When you click on that, it should give you the result. Let's see if you are getting any error here. So now you see, it says your results are below result probability. We are not getting our result probability. We will see that. Why are we not getting that here in this case? It's okay, but the uploaded audio is 98.51% likely to be AI generated, and you can listen to your audio also.
I think generative artificial intelligence will continue to improve in its ability to create real.
Fantastic. We have our waveform, okay, of amplitude versus time using Plotly Express. We have a disclaimer that these classification or detection mechanisms are not always accurate. They should be considered as a strong signal and not the ultimate decision makers. Fantastic, isn't it? So if I go back here, guys, okay, here, okay, why are we not getting it? Okay, now let's come back here on the screen. Let's do a rerun. When I do the rerun, what it will do, let me just click on analyze audio because now we have a condition there, and now you can see the result probability here, 0.985%, which is 100% correct in this case, because the audio has been taken from this deepfake video that I have created last month. If you are interested, please go ahead and create a deepfake, guys. Okay, now let's upload some other audio here also. What can I upload in that case? Let me upload this Einstein AI. I don't know if you have gone through other videos on my channel. Okay, I have created a lot of videos that might help you in your current thing that you are doing. See, I have a source of Einstein. Okay.
Artificial intelligence marks a monumental
so this is again by AI, guys. Okay, and this video, if you want to create something like that as well, please go ahead and watch this video called Digital Identity. Create your digital identity combining Midjourney, voice cloning, and Chat GPT. Here also I have done voice cloning. So let's upload that and see what we are getting. 41%, guys, to be AI generated. This is mind blowing, isn't it?
The advent of artificial intelligence marks a monument.
You can see what kind of result we are getting. Such a fascinating result, because we are reverse engineering that process, isn't it? I already have done this. If you come on my videos here, okay, I have a video called, let me show you that video. Okay, I have a video, for example, I think I came down here. Okay, now if you see this video, image to text prompt, reverse engineering AI generation, AI image generation. We are only talking about text to image using stable diffusion or DALI or whatever. Why can't we reverse this process? Okay, so this is what I am doing, right? So remind me later. Okay, so you can also watch this, and this video that I'm going to upload now for this application is going to be a very handy tool if you want to find out, because deepfake is a problem in the United States itself. 116 million fraud has been done in the last few years using deepfake, because, and that's why AI godfather Jeffrey Hinton was saying right recently that he has this concern that fake information will be available on internet, with this kind of generative AI models that we have, fake audios, fake videos, fake images, such a fake information. How would you find out if some data is is being AI generated or human generated or something, right? Now let's upload this Trump or something, which is from this video here, Donald Trump. He's talking about something and we have taken that video. If I click on analyze audio now, you will be able to see for this one it would be more inclined towards human. You can see the uploaded audio is 0% likely to be AI generated. Fantastic. Okay, you can also listen to that audio over here. Let me play that.
For President of the United
He's talking
States,
something about
we
some China and stuff that he always does. So you can listen to that here as well. We have a waveform, very interactive waveform using Plotly Express. You can also add a couple of other things as well. And I hope you like the explanation also, guys. Okay, on autoregressive and encoder and all those things over here. I hope you like it. It's very important for people to understand. If you're not understanding the theoretical concept or the intuition behind some models, it will be very challenging for you if you want to make a career in AI or machine learning or data science, guys. You have to understand how it works, because it's moving so fast. If you don't understand, it will be very difficult for you to build something like this or create something like this. So this is what I wanted to do in this video, guys. I hope you like the video. Let me know if you are facing any error or challenges while running those code files. I can help you debug those. If you have any thoughts, other thoughts or feedback, please comment it down, okay, in the comment box. You can also reach out to me. Okay, so that's all for this video, guys. Hope you liked the video. If you liked it, please show some love by hitting the love icon, like icon, sorry, and you can also share this video with your friends and to peer. Okay, if you haven't subscribed the channel yet, do subscribe the channel. I'll create more content like this, guys. Thank you so much for watching. See you in the next one.